For a reaction, we have already found the differential rate equations. On integrating the differential rate equations, we get the integrated rate equations. And these integrated rate equations are different for the reactions of different reaction order. Suppose we consider a reaction in which reactants give the products. Then the rate of reaction will be equal to negative of the rate of change of concentration of the reactant with time, and this will be equal to the rate constant K into the concentration of the reactant and the order of the reaction. X is order of reaction and it is experimentally determined value. So first we take zero order reaction. For zero order reaction, X will be 0. So rate minus dr by dt will be equal to K into r raised to power 0, and this r raised to power 0 will be 1, so it is equal to K. This implies that minus d of r will be equal to K dt. On integrating, it will be minus of r, that is equal to K into t plus c. Here c is the constant of integration. Suppose this is the equation number 1. Now, taking the initial condition that at time t equal to 0, the concentration of the reactant is R0. And substituting the value in equation 1, we will have minus R0 equal to K into 0 plus C. This implies that C is equal to minus R0. And substituting the value of C in equation 1, we get minus R is equal to KT minus R0, or R is equal to minus KT plus R0. This is the equation number 2, and this is the equation of a straight line. That means if we draw a graph between the concentration of the reactant with time, then slope will be minus K, because this reaction, if we compare with the equation of a straight line, then slope m is minus K, and the intercept on the y-axis is equal to R0. So graph will be the inclined line with negative slope. This have the slope equal to minus K, and the intercept on the y-axis, that is the concentration axis, it is R0. Now using the equation 2, we can find the rate constant. Equation 2 is concentration R is equal to minus KT plus initial concentration. So KT is equal to R0 minus R, and K is equal to R0 minus R by T. This is our equation number 3. And using this third equation, we can find the half life of reactant. That means the amount of the reactant decay 50%, the time is called half life. That means if for T is equal to T1 by 2, this is the half life, then concentration of the reactant will become half of the initial concentration. And if we substitute the value rate constant K, because rate constant is same for the particular reaction, it will be R0 minus R0 by 2 divided by T1 by 2. This is the half life, or K equal to R0 by 2 by T1 by 2. Hence, half life period of the zero order reaction will be R0 by 2K. This is our equation number 4. From this equation, we can say that half life is directly proportional to the initial concentration of the reactant. Some common examples of the zero order reactions are some enzyme based catalyzed reactions. Also, the reaction occurring on metal surface at high pressure.